this time we're going to have a closer look to how we can work with mapping, and especially when it comes to mapping frequencies of an oscillator node. That makes it possible to not just slide around on the frequency spectrum, but rather to make a jump between steps. And that is actually what we often do with music. So we pick out some frequencies we love, like a major scale or a minor scale or whatever steps we would prefer, and then having the frequencies snapping to those values, which is actually what we do when we sing. We don't just woo, but we pick da 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 like that. So this tutorial shows you how to do that and how to write different scales, and it's quite a powerful tool actually. So let's have a look. The example is found here in mouse control mapping to scale steps. Just a quick look at the overall structure of the XML data first. We have the mandatory audio element, and inside that element is a chain element, and inside the chain is an oscillator node and a gain node. And if that is confusing to you, have a look at the previous tutorials and you will understand. We will just use the gain node here to make the sound when I click with the mouse. So it's following the pointer down, either a mouse control pointer or a touch event. And it will be quiet from the beginning because the value is set to 0, and when the pointer is down, then that value will be changed to 1 and then back to 0 again. So it's a gate controlling the sound, so we don't have to turn off the volume to not get mad. But let's have a closer look at the oscillator node now, and especially at the frequency attribute. So as I did in the previous chapter, I'm following the relative x value of the mouse. So when the mouse is like here on the left side of that HTML element, the relative x value of the pointer is 0, and when I move it, it goes towards 100. So that's what we're interested in. We have an incoming variable between 0 and 100, which should be mapped to something musically useful. And in the previous example, I showed you how you can map it from like one frequency to another frequency. But this time we will use MIDI notes instead. So we're referring to like pitch numbers or key numbers in the MIDI specification protocol. And there are lots to read about that on the web, but just to give you a rough idea, if you have a MIDI keyboard with like 5 octaves, or actually I think most keyboards you buy like for your computer, your lowest note will most likely be a C, and I think it sort of always, at least very often, is the MIDI note number 36. That makes the sort of middle C having the number 60. So that's just something someone came up with a number of years ago. So just live with it. There is a very, very potential note, a low potential note called 0. And there's a very, very high potential note called 127. That's what we're giving by MIDI. So let's stick with that and just use that creatively, well, doesn't matter. Anyway, so we are mapping the incoming value of 0 to the outgoing value of 36, which is that sort of semi-low C note, the lowest key on the MIDI keyboard we bought for our computer. And the incoming value to 0 sort of goes out as number 36. And if the incoming value is 100, which is on the right hand side of my area here, the outgoing value will be 72. And because there are 12 steps in each octave, that means that the first octave will be 36 to 48, and then 48 to 60, and then 60 to 72. So we have a range here with 3 octaves. And in previous examples, the 5th value was like a power value controlling the exponential curve in the mapping. But if I type MIDI here, then the conversion will use the MIDI protocol to find frequencies that matches those key numbers. So let's have a quick listen to this. Okay, 3 octaves with notes. If I don't have this third variable, we will have all the semitones played. So let's listen to that. And if we have this steps attribute, we can specify not only semitones but an asymmetric or whatever kind of selection of steps within the range. And this is the concept. We have sort of a list of numbers. They could be comma separated or space separated. The last number will control the range over which this series of number will be repeated. So this will be the typical way of declaring a heptatonic scale, and in this case a normal major scale. So because an octave is 12 semitones, that 12 there mark out that this pattern will be repeated in octaves. And the pattern is described as semitones from the bass note, and the bass note here is 36. That means that the first note we have is 36. The next one is 36 plus 2 equals 38, and the next one is 36 plus 4, which is 40, and so forth. So we have steps with these these numbers as like offsets to the base number that we have. And then as soon as it reaches the last number, 12, the pattern will be repeated over again, but from the next octave. So that means that we will have 36 plus 12 plus 0, which is then exactly 48. And then 36 plus 12 plus 2, which is 50, and so forth. And that gives us a major scale in the next octave. And when that octave has finished, then the pattern will be repeated again. So this gives us a major scale repeated in 3 octaves. Listen. Okay, I realize that the sine wave is a bit unclear in my computer speaker, so you might have to use your headphones to hear the low pitches really well. Let's make a change here. Let's go from 60 to let's say 84. That gives us 2 octaves in a higher range starting from the middle C, still playing the major scale. That's 1 octave. Okay, that's the second. If we want to go minor, we do ba ba ba. So that's the third, and that should not be 4 semitones from the root note, but 3 semitones. That makes it a minor third. Do 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 do. We don't want to go a major 6, but a minor one, which is then 8. Da, and the minor 7th note is 10 semitones from the root note. That makes it like that. Let's listen to it. Okay, if you want to do like any other scale, like melodic, this is melodic minor, would be, sorry. It's kind of majorish in the end, isn't it? So you could do any scale, but by just changing those values. And you could be super creative as well. If you want to like lower the 5th a little bit, you can just do like 6.8 instead of 7. It's now a bit lower, right? You can make it really ugly as well. or ugly. That was very sort of narrow-minded approach to frequencies, wasn't it? But some people think that was ugly. Anyway, so that was the real minor melodic scale. That makes it possible to actually do like just temperature, or what do you call it? Just intonation, just tuned scales by using any decimal numbers here. You can do also really creative patterns doing it like this. That will be a very short scale, repeated in whole tune steps, playing like the root note and then repeating itself 2 semitones above, which is then a whole tone, and then repeating itself two whole tone steps. So this is a whole tone scale. And you could do the similar thing with like thirds. So this will be stacked minor thirds. Or do this scale, which is first playing the root note and then 2 semitones above, which is a whole note, and then repeating the pattern but with the interval of a minor third, which actually creates a diminished scale. You could do pentatonic scales like do, 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 do. So this is a major pentatonic. Or a minor one. Do, 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 do. Sorry, I have to sing when I write, otherwise I'm totally out of numbers. And of course you can add the number 6 here and you get the blues scale. It's quite a fun way of playing around with scales, I think. Makes it quite sort of connecting my math and my music brain at the same time. So I love it. Try it out.